Hi folks, how you doing? So let's just we're continuing with differentiation topic, and it is pretty basic. So we'll no go over the top here. So we'll just try to go through the things that we need to know. So we spoke about derivatives being, or the derived function being the gradient function. Okay, and so that's we're just going to continue with that theme there. And we emphasize that this word, this phrase, rate of change, it's always going to come up here. So we're just relating gradients, um, being specifically the tangent on the curve, or the tangent line to the curve. So let's get a picture, that's better. So y equals f of x, so f of x, that refers to some kind of curve, doesn't necessarily have to be a function. Um, but as long as we can describe it using some kind of mathematical notation. So here, select a point on this curve here and slap a line on it. And there, we saw it earlier, or we described earlier, that the gradient of the tangent line is identical to the gradient or the rate of change or the steepness on the curve. So So what we can do here is just pick a specific value. I'm calling it A here or whatever. We're going to have a number, and we'll just fire that value A into the derivative, and that will give us this steepness. So we've got a function. So what we need is a derivative. I'm using M to represent gradient, and I'm using the dash notation here. So on the left hand side, hopefully you can see I'm using the F notation here, right? And I'm going to get the derivative of the gradient and the F notation here. So you're thinking, well, how come X is turned into A? Well, that's because I'm declaring that X is actually equal to A in this case. So that's where that came from. Okay, right. So yep, let's go for a nice wee example. So f of x, or y equals x cubed. I'm using the function notation here because I'd like to I'd like to see the value of x I'm going to put in here. And so value the gradient, the tangent line of the curve, x cubed at x equals 1.5. So if you want a wee picture of that there, the curvy part, um, y equals x cubed, f of x equals x cubed, that's fine. And I've selected a value on the x-axis of 1.5, and I've just went up vertical from there till I hit the curve, and I put a tangent line in there. So the steepness or gradient for both the line and the curve are identical here. So let's go and get a gradient. There's my function, f of x equals x cubed, y equals x cubed, doesn't matter. Let's differentiate it. Okay. 3x squared. You've done that before, no point going through it. Bringing down the power in front of x and reducing the power by 1, that's fine. So that's our derivative of the original function, 3x squared. Okay, so we want to evaluate it at 1.5. I'm just specifying there, or reminding you that m is actually the gradient, and so I'm using the f dash notation here. So in place of x, I've actually put 1.5 because that was a specified value there. So wherever we'll get x within 3x squared, replace it by 1.5. That's exactly what we've done there. So you can type in 3 times 1.5 squared, or you can type it 3 open bracket 1.5 close bracket power 2 equals, and it will give you, what's that, 1.5, 1.5, 2.25, 6 point, 7.5, something like that. Right, there you go. That's it, folks. That's the steepness of the line on the curve, or both. That is it. Okay. Another question here. This time we're changing the type of function that we have here. Sine x, so that's one of the wavy things. And the point I'm looking at is pi over 3. That's fine. So I'm looking at the gradient at a specific value, x equals pi over 3 on the curve y equals sine x. So this sine x between 0 and 2 pi. We're all up to speed that 0 to 360 degrees is identical when we go to radian measure of 0 to 2 pi. So halfway with the pi, so 0 to pi, so I'm going a third of the way to get pi over 3. So pi over 3, there you go. Go up to the curve and get a point, then slap a line on it. Get a tangent line on there, so to indicate the steepness. Yep, okay, I can see that there. And just been looking at that line, one thing I know, it's rising from left to right. I know the value is going to be positive. Right, okay, so we don't need a graph, but sometimes it's good to have knowledge of the graphs, just to see what's going on here. So we're trying to evaluate the steepness of that line, the tangent line, steepness of the curve at x equals pi over 3 on the graph y equals sine x. Let's go through the motions. Okay, there's a curve, let's differentiate it. That's our basic one, y equals sine x, dy by dx, or y dash is cos x. Okay, that's my derivative. Let's go and get our value at pi over 3. Let's fire that in there. Y dash equals cos pi over 3. So, I'm just going to type in here. I'll type, because I don't have my pen. Let me just pull that up there. Right, so that might mean, I'm saying working radian measure, that might mean changing your calculator into radian mode. Yeah, that's what it might mean to you. Okay, that's fine. Don't worry, I might as well update my notes whilst I'm here. There you go. So you can change your calculator into radian mode, or you might get away with it by knowing that pi over 3, pi is equivalent to 180 degrees in degree mode. So that'd be 180 degrees divided by 360. You could get away with it here because I don't have plus or minus after the x value. So I put that in, I get a half. Hopefully you get a half. So that's what it's telling me. The gradient of that line has steepness a half. Right. Remember to work in radian measure here. Right. Okay. Here we got another one. Doesn't matter. We'll get whatever the variables are here. We're matching up Q. The variable's actually T here. So what they stand for. But what I can see is that I've got a trig function here, and see the stuff in front of t, that is just a number. 2 pi, it's just a number, like 6 and a bit, 6.28, whatever it is. It's just a number. T plays the role of x here in this. Right, there you go. That phrase there, rate of change, comes up. Rate of change with q with respect to t. So let's go and differentiate Q here. Okay, but they've given us a specific value because they are actually looking for the rate of change. Don't get ahead of yourself there, Tommy. Right, okay. Okay, so you could use Q dash or dq by dt because t is the other variable that's linked in here. So it's a change in Q over the change in T, dQ by dt or Q dash, whatever I put. There you go. And when we're doing this, just remember, it's a value in front of our variable. That's going to come out the front there, okay, to multiply the 10, and then we just need to think what happens with cosine. So cosine goes to negative. 2 pi times 10 is 20 pi. Cos goes to sine. The stuff inside the bracket stays the same. Okay, we've differentiated it. Right, so now we need to have value. We've got time there, 0.75 seconds. So in place of t in the bracket, 2 pi will go in front of that. That's fine. I've just put another wee bracket in there for safety. Right, that's what brackets are there for. Put it in. I've probably what have I probably done? I know what I've done, but I just want to show you what I've done. See the 2 and the 0.75, because they're kind of similar type of numbers, rational numbers, whatever you want to call them. I've multiplied them together. Okay, so 2 times 0.75 is 1.5. That's why in the next line I'm going to have 1.5 stuck to pi, right? Just in case you're having a wee panic attack, right? Now you should be able to type that in your calculator there. Negative 20 pi sine 1.5 pi. Remember to be in radian mode. And hopefully we're going to get negative 20 pi. Oh, sorry, positive 20 pi. Because the sine of 1.5 pi is negative 1. We've got that there. And maybe your calculator depends what mode it's in. And it might give you a decimal answer. So 20 times 3 is about 60. So 20 times 3.14 was 62.8 approximately. Right. Forgive the scribbly writing there. Just using that not so magic pen. That'd be fine. And do we know the units of measure here? I don't know. What is coulombs charge? What is the definition of it in relation to time? So the change in charge in relation to the change in time. I'll let you go and have a rethink about that. We're just moving numbers about the page. Okay, so that looks fine. Right, here's another one. Looks as if I forgot to scratch a pen out again. Determine the rate of change of what we've got there. That's V equals 100 sine. Inside the bracket is 5 pi t. And we have a value of 0.1 seconds representing t. Let's go and get a derivative. So dv with dt or v dash, whatever. Bring the 5 pi out the front because 5 pi is in front, okay, of the t. That's playing the role of x really. So it's 5 pi times 100 there. And just remember that when we're differentiating, sine goes to positive cosine, and the stuff in the bracket, all that stuff there, stays the same. Okay, then it's just going to be a matter of tidying up. Okay, 5 pi times 100, 500 pi. Still got a cosine, still got 5 pi t, and so that's just got a derivative. So what did we have for t? I think it was 0.1 seconds. So in place of t, we're going to have 0.1. Yep. And I think the two things that can interact here are the 5 and the 0.1. Going to do that. Yep, they're going to interact. And whatever 5 times 0.1 is, stick that in front of pi, and then it's calculator's time. Okay, calculator time. So just type in 500 pi or 500 time pi times cos, open the bracket, 0.5 times pi close bracket, again being reading mode here, and don't be surprised if you get an answer of 0. Right, that's fine, because the cosine of a half pi is 0, and anything times that is going to be 0 as well. Right, okay, so all this goes back to the kind of first lesson where if it was sine or cosine, we showed you the little rules. All we're doing here is sticking a number in at the last point to get this rate of change. Okay, get a derivative, put the number in, that should be the rate of change. Okay, right. So stationary points, what you think about here? Points that don't move, and you're thinking, well, none of your points ever move on that page. Well, stationary points, they're different kind of beasts. Right. So we're just going to go through what are stationary points. Well, they're specific points on a curve. Okay, I usually hate that word function. Right, we just talk about on a curve where the derivative is exactly 0. So if I put a line on a curve and that line was horizontal, then its derivative would be 0. Okay, so that's what that's in there. That's very important. That's a condition for finding stationary points. So whenever they talk about stationary points, get a derivative and set it equal to 0. We've got different types of stationary points, so I'm just going to go through that. I've probably seen this in the past. That looks as if it's almost parabolic. Doesn't have to be, but they call that a local maximum. Um, and this one here, that looks parabolic, where it bottoms out here. They refer to that as a local minimum. This one here, from the left to right, it goes up, kind of levels off, but then starts to increase again. But at a certain distinct point, it looks as if it's horizontal, and its partner in crime, it's just coming down the other way. It does likewise, so it comes down from the top left, kind of levels off, so it is horizontal at a certain point before it starts going down again. So we get 4 kind of types of scenario here where stationary points exist. But the thing is here that at every single one of them, the derivative is 0. And I'm connecting these with y and x. It's like your normal Cartesian coordinate system of x and y. Okay, that's the gradient. Remember, changing y over changing x, that's the gradient. These are 0. Okay, let's go for a little question here. We've got a little function, y equals x squared taken by 5x plus 6. So we're going to locate the stationary point, and they're asking for the x value of the stationary point here. As soon as they mention stationary points, think 2 things. Think derivative, and then think about making that derivative equal to 0. Let's go and get the derivative of x squared taken by 5x plus 6. That shouldn't be too difficult. Use the rules. That's your derivative. Okay, right. Stationary point, derivative, condition. That's a condition. Stationary points exist where the derivative is equal to 0. Okay, so we'll get 2 things here. We'll get 2 expressions for the derivative. We'll get that one there. We'll get that one there. So why don't we take that there and make it equal to that there? Because they are identical. They are both expressions for the derivative in this problem. That's exactly what we did there. Go and solve for x. Okay. I don't think I'm going to have to talk you through that. You could have written that as 5 over 2. That is fine. So what you've done is you've answered the problem. You've found the x value of the stationary point. That is it. Right. Okay, let's go for another one. We've got another function. relating y and x. 2x cubed take away 15x squared plus 36x. As soon as they talk about stationary points, trigger points here, get a derivative, set it equal to 0. Right, we'll get a function, y equals something in terms of x, differentiate it. Okay, shouldn't be a problem. Next thing, state your condition. Okay, it's always good to state that. That is a trigger for what happens next. Take your derivative and make it equal to 0. Right, that's a quadratic equation. You go and solve it by whatever means you find easiest. The way I'm going through this here is I spot that each of the coefficients, the 6, the -30 and 36 are all divisible by 6. So that's what I've done. See, when you get 0 over the other side, it's great. You can multiply or divide both sides by whatever part of the 0. And you're fine. So I've done that. And the reason I've divided it by 6, it's just to make it easier. You could have used the quadratic formula there, or you could have factorised it there. I brought it down to there because that looks like it's for me anyway, and for you, because you know all about factorising these days. You can factorise that, so why don't you? Yep, don't ask me how I got that. Go and look at your notes. Okay. So you get one bracket times another is equal to 0. The only way that is possible is if the contents of one bracket is equal to 0 or the contents of the other bracket are equal to 0. Now, let's go and solve for both. Let's isolate x. So x take 2 equals 0 means x equals 2, or x take 3 equals 0 means x equals 3. And I say take, I mean subtract. Right, there you go. You've found the two x values of your stationary point. Sorry, the two x values of your stationary points, plural. Right, okay. Dealing with a home run here. I want to make this one a little bit shorter than the last one. Same again, stationary points. Got some kind of function here, curve. Well, we can have a graph of it. I could graph that. X to the 4 take away 8x squared. Again, as soon as they mention stationary points, think derivative and think about making it equal to 0. Go and differentiate that. 4x cubed take away 16x. That's what I think I'm getting if this thing is going to behave. Yes, it is. Okay. Got derivative condition. That stationary points exist where the derivative is equal to 0. Okay. Let's go and make it equal to 0. Done. Look at the left hand side, 4x cubed take away 16x. I think I can factorise that, unless you're good at solving cubics. I don't know, you might be. To get a common factor of 4x, because both are divisible by 4x, what have I got left? X squared take away 4. I can factorise that, I think. But I'm going to separate and solve. So I'll get something times something is equal to 0. So I've got that times that is equal to 0. The only way that it's true mathematically if one or both are equal to 0. So I'm going to separate and solve here. That's what I've done. So 4x is equal to 0. How can I solve that? We'll get rid of the 4. Just take over the other side and divide, or divide both sides technically before. You get x equals 0. Other side, x squared take away 4. That's a difference of 2 squares. I could have solved it like that there. Or I could just get x squared on its own, because I don't have any other occurrences of x, because I've done that. X squared equals 4. Let's unsquare it. Take the square root of both sides. Because I've got no real context here, we don't know if we're talking about a measurement, a length, or a depth, which means the answer would always be positive. So I have to take cognizance or notice there's a possibility of two answers here. So when I hit square root of 4 on the calculator, that will give me 2. So the answers are positive or negative 2. So if I actually get two answers here, I got my 0 answer there. So just let's bring them all together. And that's what I've done there. And on my next page, just bring them all together. They're not asking you to do anything else here. look at the nature um, of these stationary points, whether they're local maximums, local minimums, um, falling or rising points of inflection. That's all they want you to do here. That is it. Right. Remember, you've got the power of the button. You can turn me off or you can rewind. Okay, here we go. Determine the rate of change of A depending on R. That's the thing in the bracket. Is pi r squared. Oh, you might have heard of pi r squared. So at a value r equals 5 centimeters. Right. Rate of change. I need to differentiate. I'm using a dash. So, oh, how did I get 2 pi r? Oh, that's mathematics. Well, bring the 2 down in the front. Okay. Reduce that 2 by 1. Okay. So all we need to do now is put in the value of r, which is 5. Okay, that's why we're using the function notation, the bracket notation here. So the derivative of a, that's a dash, at 5 is 2 times pi times 5. Okay, if you put that in your calculator, it'll probably give you 10 pi, something like that. That's fine. Or you might decimalize it, and that's like 10 times 3 in a bit. So it'll be 30 in a bit. 31.4 approximately. 31.42. That is it. That looks okay. Let's move on with another one involving pi. Determine the rate of change of v of r. That's what it means. V uh, is depends on r. 4/3 pi r cubed. Okay. So here, this part here, that's just a number. That's like the number in front of x. So what you want to do here is just bring the 3 down the front. Bring the 3 down the front, and that will times the 4/3, and hopefully that will sort itself out. What's 3 times 4/3? Hopefully you're seeing 4/3. That's just 4/3 times pi r squared. Right. And I'm just going to tell you this anyway, just to annoy you. See that part there? That's actually the working out the volume of a sphere. See when we go downstairs and get its derivative? That's actually the surface area of the sphere. So see when you're differentiating kind of geometrically, when you differentiate, you drop a dimension. So we have actually went, I don't know if it's apparent, so volume, you might think volume is 3 dimensions, we have went down to 2 dimensions. So we actually went from volume of a sphere down to the surface area of a sphere. Don't have any bad dreams about that. That is fine. So I'm going to finish that one there, folks. And hopefully it wasn't too painful. And you can have a wee think about this, what this picture represents. But don't you worry too much about that. If you think you know, let me know. Okay? Right, bye for now.